Hi everyone, welcome to this video, and today we'll be working on proportional and integral controllers, or PI in short, and we'll be solving a question in both frequency domain and time domain. So let's get it started and dive into the first question. The first one is saying plot the bode plot for a proportional and integral controller where P is 2 and I is 0.02. The controller has a transfer function of obviously P times I plus S divided by S. So this is a hint to give us an idea about how does a PI controller in frequency domain look like. So as we have discussed extensively in our previous video, how to deal with bode plot of different transfer functions, we will follow the same rule, but this is only an example of a generic transfer function that we still need to break it down into simpler pieces. So if we think about how this transfer function can be split into smaller pieces, I'm going to ask you to replace the numbers in order to make sure that everything stays the same. 0.02 plus S divided by S. So we eventually need to convert both poles and zeros into a form that we see 1 plus S over something. So that something becomes our critical frequency or cutoff frequency. Here, by the way, we're not dealing with 1, but instead we have 0.02, which means that we need to factor from 0.02 at the first place. So if you factor 0.02, what is left is 1 plus S divided by 0.02 divided by S. So this is the generic form that is acceptable for S, since both poles and zeros are in the standard form. We can further simplify this multiplication, and we can get 0.04 multiplied by 1 plus S over 0.02 divided by S. So essentially, we're dealing with three different parts. First is this coefficient, which is a constant number. Then we have a zero that is happening at a frequency of 0.02 as the cutoff frequency. Then we have a pole at origin. So we need to plot three bode plots and then sum them up together at the very end. So let's start with the first one. If you call this as H, I would say H is a multiplication of H1 times H2 times H3, which in our case H1 is simply 0.04, H2 is 1 plus S over 0.02, and H3 is simply 1 over S. So these are the three different smaller transfer functions that we are interested to plot them. I'm going to change the colors for each one of them so that it will be easier for us to recognize which is which. So this one can be in black, and the last one can be in green. Okay, so let's start with the first one as H1, which is a constant number of 0.04. So we just need to get 20 log of that in order to make the bode plot of H1. So 20 log of 0.04. So if you calculate this, you would get to a value of around minus 28 dB. So that means that we need to just plot a constant line at minus 28, roughly here, that doesn't depend on frequency. So this is actually H1. Now, moving forward, we can think about H2, which is essentially a zero, but that's happening at frequency of 0.02. So if you want to find out what is frequency of 0.02, it's so this is 0.01, and here is 0.02. So let's label that 0.02. This is the frequency of interest. Now, we know that this zero has a generic shape that is high pass, and the cutoff frequency for that is going to happen at 0.02. However, before that, everything is going to be 0 dB, and above that, it's going to be plus 20 dB per decade. So essentially, we are having something like this, in a sense. So let's plot this, and all of the low frequencies are going to be 0, and high frequencies are going to be 20 dB per decade, which is over here is at 0.02, over here it's going to be 0.2, and over here it's going to be 2 and 20. So if we plot this line and connect all of those dots, that would be our high pass filter characteristics for this 0. Now we can label that to be H2. Now moving forward, H3 is essentially 1 over S, which is a famous singular case. In this case, because we don't have exact value of the um, pole visible in our log scale, which is the 0, we just need to think about another method. And as we discussed, we need to find out that this 1 over S is going to pass through a single point that we need to determine that. And obviously, the slope of that line is going to be minus 20 dB per decade. The easiest point for us to determine is going to be 1, because if you replace 1 as S equals 1, then 20 log of 1 over S, when S becomes 1, is simply 0. So that takes us to 1 and 0. At the frequency of 1, the 20 log is going to be 0 dB. So frequency of 1 is going to be here, and 0 dB is this value. So we need to plot a line that crosses this point, but has a slope of minus 20 dB per decade. So if we think about this line, this is our 1 over S, or in a sense, H3, that has minus 20 dB per decade slope, but minus 20 dB per decade slope, while it crosses frequency of 1 and 0 dB. H2 actually had minus 20 dB, well, plus 20 dB per decade. Now is the time to just sum them up, and we can start all the way from the lower values. So essentially, this blue line is a constant value, and the value is minus 28. This one is 0, and this only offsets all of the characteristics by 28 dB in the negative direction. So now that we have 60 dB at the frequency of 10 to the minus 3, we need to bring it down to about minus 28 dB lower. And in doing so, we will be left with 32 dB. So 32 dB is where we would need to start. It is essentially 60 minus 28, which is 32 dB. Now, we need to then follow these slopes. These two black and blue lines are going to have a slope of 0. However, this green line is having a slope of minus 20 dB per decade. We will follow minus 20 dB per decade until we hit the first critical point. And over here, this is the frequency that has the critical point. So it means that we need to move down all the way to around here. We need to be, we can always calculate the numbers to be a little bit more accurate, to be that of what happens at this specific frequency, but we can always roughly sketch it, and it wouldn't matter significantly. Now that we have hit our first critical point, we need to consider what is the change in the slope afterwards. We now have a new line that has positive 20 dB per decade, and that is going to cancel out this green line with minus 20 dB per decade. So essentially, summation of these two would result in a slope of 0. And our blue line had already have a slope of 0. So we would have a total slope of 0 from now on. And if you consider what is the frequency that this situation is going to break down, apparently in this case there is no other frequency, because at all other frequencies higher than 0.02, the slopes are going to be cancelled for black and green ones, and the blue one has always a slope of 0. So it means that our high frequencies are going to stay at this level almost all the time. So that will be our characteristics for the gain, which goes back to the total H in this case. So here is H, and remember that this piece had minus 20 dB per decade. So now let's start working on the phase diagram, though. Again, we're dealing with the same set of H transfer functions, and we need to, again, plot the phase diagram of each separately and then sum them up. Starting with the first one, since this is a positive number, it has a phase of 0 across all frequencies, regardless of the frequency value. So I'm drawing H1 as 0 phase, regardless of the frequency. Now, let's move on towards the second one, which is a 0, and the frequency of interest is going to be 0.02. So essentially what happens in a 0 is that at exactly this frequency, we have a phase of plus 45 degrees. And 1 decade higher than that will reach to plus 90 degrees. 1 decade lower than that will reach to 0. So we need to identify this cutoff frequency 1 decade after and 1 decade before that as well. So 0.02 is going to be this frequency, 0.02. 1 decade higher than that is going to be this, which is about 0.2, and 1 decade lower than that is going to be 0.002 here. So the phase at 0.02 is going to be exactly at 45 degrees, which is here. It's right on the top of the curve. 1 decade before that is going to be 0. 1 decade after that, which is going to be out of the screen, it's going to be plus 90 degrees. So we would be around here to be plus 90 degree. So if we connect them together, we would have a straight line like this. And higher frequencies are going to be again a straight line, and the lower frequencies are also going to be another straight line. Now, the third one, let's call this actually as H2 as well. Moving towards the third one, this is 1 over S, which essentially is going to have a phase of minus 90 degrees across all frequencies, because 1 over S is essentially 1 over j omega. And if you think about where it stays, it's all about a vertical line that, regardless of the frequency, it considers this line, and all of the phases are going to be minus 90 degrees on that vertical axis. So a constant minus 90 degrees is going to be the phase associated with this H3. Now's the time to sum them up and come up with the total phase. If you think about what is the initial value that we start with, so two diagrams start with 0, and their summation is going to be 0. But then the third one is minus 90 degrees, which means that we have to consider minus 90 degree as our starting point. Now we will keep moving until we hit the first critical point. As you can see here, it's going to be 0.002. At this point, we need to follow the slope, and this slope is going to be plus 45 degrees per decade. So let me just write it down as well, that this is plus 45 degrees per decade. So we need to actually consider the same scenario. We'll start all the way from until hitting this critical point, then we'll have the same slope of 45 degrees per decade, which is going to be here. So we have moved up by 90 degrees as long as we have moved by 2 decades. So we can easily monitor that here as well. So, at the higher end, we have 90 degrees difference. So this is 90 degrees. And then after that, we again hit the critical point. Then we need to consider again the summation of all of the slopes. This has a slope of 0 plus this slope, which is 0 plus this slope, which is 0, which means that we need to consider a 0 slope from there on as well. And with that, this would become our total phase diagram for this structure. So that is how we could get to the phase diagram of this PI controller in frequency. So let's move on to the second question, which is an interesting one, and following up the same PI controller, but this time in time. Now the question is, a PI controller has a gain of P, the same information, the value of the initial output is 32% at t equals 0. Plot other graph of a controller output given the following graph of the error. So essentially what it really means is that when we are feeding this controller, this PI controller, imagine that here is the PI controller and the input of that is this E. This output, or C, is going to be calculated, but this time it's going to be in time. Now, this E is already given here as a function of time, or the error. PI controller is the one that we discussed in the previous slide in frequency domain. Now, we need to consider that in time domain. So let's start actually discussing the equation of the, well, let's call this V, the output of the PI controller. What is the output of the PI controller with respect to E? We know that the PI controller has PE plus PI integration of E dt plus V naught form with respect to time, which means that we have both proportional component as well as integral component plus an initial value. So this is the output of the controller. The question itself states that the value of the initial output is 32% at t equals 0. It essentially reminds us of something that is related to this V naught. We just need to consider that what is V naught at t equals 0. So essentially, if you equate this equation with t equals 0 and calculate the values and evaluate of V, you would get to P times E, which is 0 at that point, as you can see from the input as well. So the error is 0 at the time 0. And essentially, this PI is going to be multiplied by the integration of 0 dt plus V naught. So essentially, what is left from this equation is only V naught. And this suggests that this 32% that we had from the question is essentially V naught. So V naught is 32%. Now, let's move on and try to calculate the rest of the output. By the way, we need to be mindful that let's put a dot as 32% here. That shows the controller output in percentage as the starting point, actually. The next points in time are going to again be plugged in the same equation. So let's try to calculate the error at time equals t equals 20. So at t equals 20, what happens? We now know what is V naught. We need to also be mindful that error at this point is going to be 10, because that is the time that there is a jump in the error all the way to 10. But there's nothing before that, actually. So at t equals 20, the error is going to be 10. And by the way, the integration of e dt all the way from 0 to this point is going to be 0, because essentially there is nothing at that point. So this integration is going to be 0. Now, if you plug in all of these numbers into the main equation, we have p times e, which in this case is going to be 10, plus pi integration of e dt, plus v naught, which is going to be 32. I would rather call this error, or the output of the controller, in percentage in general. So since the error on itself is in percentage, so we can assume that this 32 is going to be 32 rather than 0.32. So essentially, since this error is in percentage, we also consider the 32 at this point. Now, we know that p is 2, so we can replace p with 2 as well. And also we know that this integration is going to be 0. Then essentially the output is going to be 20 plus 32, which is 52. So we essentially have the value of 52 at the location of 20. However, before that, we didn't have any value. So we're dealing with a sharp jump at that location of time. Now, so let me put down some numbers over here to be able to recognize what these values are. Essentially, we started with t equals 0. So if you put 0.1, here is 0.1 on this output diagram. Here, v naught as 32 is going to be again 0.1 and 2. So the third output is going to show itself here on this diagram. So, and also 0.2, the 2 is going to be here. Now, let's move forward and think about the next critical point on this input, which is going to be around 70 as the seconds. At t equals 70, t equals 70 seconds, we essentially need to consider the integration of the area E dot dt as the area under the curve. And in this case, we just need to find out what is this area under this error curve. We know that the width of this is going to be from 20 all the way to 70, so which is 50. So this width is 50 multiplied by this 10, which essentially is going to be 500. So the area under this curve is going to be 500. So if we consider the output at the t equals 70, p is going to be 2 times error. Error at the location of 70 is going to be 10, because that is clear from this error diagram, which is going to be 10. So 2 times 10 plus the area under this curve is going to be 500, but that's going to be multiplied by I and p. So I is going to be 0.02 and p is going to be 2 plus the v naught, which is 32. And if you calculate that, you get to the value of 72 for this point. So 72 takes us to 0.4. We were at a point of 52, and now we are, okay, let me put it in black to be consistent. So we are at the point of 72. Now at t equals 70, which is here, we are at this point roughly. So this is point 4, and we can connect these dots together to make a line. And also we had a jump over there. So now we are at a location of t equals 70. Moving forward, we have the next breakpoint as 80. Let's try to calculate what happens at t equals 80. Now let's think about the next points of interest over here. So we were here, right here at the t equals 70. However, right after 70, which is going to be just after t equals 70, we are dealing with a different error value. Even though the area under the curve before that is going to be the same all the way from 0 to here. But then the error right after t equals 70 is going to be 0 compared to right before 70, which was 10. That's why we need to consider this jump in the output as well, which will have a jump. So if you want to consider the t equals 70 slightly above 70, let's call it 70 plus, the modification in this is going to be v equals 70 plus equals 2 times the error. This time error is going to be 0 plus pi and integration are going to stay the same because the history of the diagram hasn't changed so far. And this summation now, if you calculate that, takes us to the value of 52. So it means that we're gonna have again another jump from 72 down to 52. So 52 is roughly again here. So it's going to be like this, which is our 5th point. Now moving forward up to 80, but at the time of right before 80 seconds, we can consider t equals 70, well 80, but right before that, so I would call it t equals 80 minus. In that case, whatever that we have had so far in terms of the integration is going to stay the same, but then the absolute value of the error is going to also stay the same. So we will have a very similar result compared to the previous step. So at v equals, let me correct this, at t equals 80 minus, we still have error 0, we still have the same area under the curve as the integration, and the same initial value, which takes us to the same output of 52. So that is our 6th point. So essentially, all the way from here to 80 is going to be the same value of 52. So this is our 6th point. Now, moving forward, right after 80, by the way, we're dealing with different error value. So this error now is going to be minus 10 compared to 0, and we are going to have another jump in the output. So t equals 80 plus right after 80, so at v equals 80 plus, we are dealing with a different error, which in this case is going to be minus 10 plus the area under the curve all the way so far is going to stay the same because we haven't had any other area other than this. So 2 times O times 2 times 500 plus 32, which is the initial value. And if you consider this, it's going to be 32 as our 7th point. So now we are going to jump all the way from 52 to 32. So 32 is going to be here. So here is our jump. Now, moving forward, So we have considered 80 plus. The last point is 100. So 100 is going to, we can think about 100 minus, which is just a little bit behind 100. We have another area under the curve, which is going to be this value as the secondary integration that we need to consider. So at that point, at t equals 100, let's consider 100 minus, let's put it this way to be more accurate. We need to consider 2 times the error exactly at that point, which is going to be minus 10 plus p times O2. Now, the integration of E over dt is going to be the area under the curve all the way from the first part and the second part. So all the way from 0 all to 100 seconds. So that's why that we need to consider both this area plus this area. But then obviously the first area is going to be positive, the next area is going to be negative, especially because the error is going to be negative in the next case. So we need to then consider 500 as the initial one, but then the second area is going to be 20 times 10, but a negative number, so minus 200. So minus 200 is going to be the area under the curve plus the initial value, which is 32. So if you calculate this, you get to the value of 24 as our last point, that I call it 8. So 24 is going to be around here. So we're having a decline in the output. So as you can see here, we have come up with a complete output of the PI controller as a result of a given error to the input of that controller. And this is how we can deal with PI controller in time domain, since we are integrating it over to time. So now that we have discussed how to deal with such a question in both frequency domain and time domain regarding PI controller, here is another example that I'm leaving it to you guys as an exercise. You're supposed to first plot the bode plot of this diagram of this PI controller with respect to the transfer function that is given, and also the coefficients and time constants that are given. Then you need to also consider the output of this error function and this PI controller with respect to the given error function in the bottom figure. So consider this as the input error and also find out what is the output of the PI controller. Thank you for watching. Hit like and subscribe to the channel if you enjoyed this video.